when being. The design of the actuator section of our wiring harness begins the same as for our sensor section, with us gathering all of the data that we possibly can on the actuators fitted to our engine or chassis. The main way the design of the actuator section of our wiring harness differs from a modified street car or club day track car is that the actuators we will be interfacing to are often more complicated and will have some specialized wiring requirements. For this reason, making sure that we have accurate and complete documentation is a must. Even if we're still interfacing to a common actuator, such as a simple cooling fan, we may want to control it in a more complicated way, varying its speed, for example. We'll look at a few examples of motorsport-orientated actuators and the considerations that we need to make when we're wiring them now. In the power supply design section, we talked about using either solid-state relays or a power distribution module to supply our actuators with power. One of the reasons for this is that the electronic switching these devices employ allow us to use pulse width modulation to deliver a varying amount of power to our actuators. If you're going to control an actuator using PWM, there are multiple factors that you're going to need to consider. The first of these is that the ECU output, which will be switching the relay or PDU output channel, is capable of PWM operation. Your ECU documentation will have this information. The second is the PWM switching frequency you'll drive the actuator at. It is possible your actuator documentation will have guidelines on determining this, but often it can be a trial and error process. For items such as fuel pumps, electric cooling fans, and water pumps, driving them at a higher PWM frequency usually leads to more consistent and smoother results. Often, the motors in these actuators emit an audible hum when being driven using PWM, which typically reduces in amplitude as we increase the driving frequency. You will be limited in the driving frequency you can select, however, by the ECU output channel, PDU specifications, or the solid-state relay switching capabilities. In all cases, the documentation of these devices will give you these limits. As an example, a commonly used Hella solid-state relay has a maximum switching frequency of 1000 Hz. Exceeding the stated maximum frequencies can seem like it's initially working, but can result in the PDU or solid-state relays overheating and being damaged, so it's not something that you should attempt. The high operating speeds and high power output of motorsports engines often calls for a more powerful ignition system than a traditional inductive coil design is capable of providing. This is accomplished by moving to an alternative ignition setup known as capacitive discharge ignition, or CDI. This system will have a separate CDI ignition driver, much like an ignition module in a traditional inductive system, and specific CDI ignition coils. Internally, the CDI driver uses a switching circuit to very quickly charge up a capacitor to a high voltage, typically in the range of 300 to 600 volts. When the EFI ECU requires a spark to occur, it signals this to the CDI driver, which then discharges this voltage across the coil primary winding, which in turn generates a much higher voltage, typically greater than 40,000 volts in the coil secondary winding. This higher voltage is more successful at igniting the air-fuel charge in the combustion chamber of a high-power racing engine. The key wiring consideration when dealing with a CDI system is that the high voltage discharged across the coil primary winding is a powerful source of electrical noise, and we need to use shielded wiring to make the connection between the CDI driver box and the ignition coils. When determining the wire to use and physically constructing the harness, you need to keep in mind the high voltages that this circuit will see and ensure all the materials have adequate electrical insulation specifications. Another actuator you will often find in a motorsport application is an electronic throttle body. As discussed in the power supply design section of the course, an electronic throttle body requires a control module to drive it correctly. The wiring of this control module to the motor inside the throttle body is fairly straightforward, typically being just 2 wires. The control module contains an internal electronic circuit known as an H-bridge. This circuit is capable of PWM operation to vary the speed at which it operates the motor inside the throttle body, but can also change the polarity of the voltage it applies to the throttle body motor, and thus its direction. Now this allows it to either open or close the throttle body plate. Motorsports have an inherent element of danger, and an electronic system often installed to help ensure driver and equipment safety is a fire suppression system. These systems consist of a pressurized tank of fire retardant, which is plumbed to nozzles situated around the vehicle. A solenoid valve is mounted on the tank outlet, which can be triggered electrically to release the fire retardant throughout these nozzles. These systems are powered by a small 9-volt battery, and when installed are done so completely separate to the rest of the electrical system in the vehicle. This reduces the chance of an error in the design or construction of the wiring harness, contributing to the system being accidentally triggered, along with the 9-volt battery power ensuring the system can still be triggered in the case of a failure with the rest of the vehicle's electrical system. Like with a battery isolator, there will be a switch within easy reach of the driver to activate the system in the case of an emergency, along with an external switch to allow a race marshal to activate the system from the exterior of the vehicle. These systems also have an arming switch. When the system is disarmed, pressing the triggering buttons will not fire the system, but will instead have the control box emit an audible tone or light an LED to check the status of the 9-volt supply battery. It is critical that when the vehicle is not being run and there is no risk of fire, this switch is left in the disarmed state, as the cleanup involved if the system is accidentally triggered is a time-consuming and expensive process.